So now that we have the theory of S equals L, D, L transpose under our belt, let's see how we can use that concept to build what's called a Cholesky factorization. So a Cholesky factorization is an equation that looks like S equals R transpose times R. So this means S is the Gramian of some matrix R, and R here is an n by n upper triangular matrix with a non-negative diagonal. So this is a very specific situation. Here I would have a real symmetric matrix factored as the Gramian of an upper triangular matrix whose diagonal has non-negative numbers on it. So of course, as soon as I know that S equals the Gramian of anything, I know that S has to be an n by n positive semi-definite matrix. So a Cholesky factorization is something that only positive semi-definite matrices have. Now, remember, if your positive semi-definite matrix is the Gramian of some matrix called R here, then the quadratic form, which has formula given by input vector inner product with S times the input vector, can be written as inner product of X with R transpose Rx. And if we move this R transpose to the left, we realize that we're looking at the inner product of Rx with Rx, which is the length of Rx squared. So this always allows us to write our quadratic form as a sum of squares. Now, another thing to remember is that this matrix S is going to always be positive semi-definite, but it is positive definite if and only if the matrix R in this situation is non-singular. So let's look at an example. Here I have a matrix S factored as R transpose times R, where R here is upper triangular, and its diagonal is non-negative. So there aren't any negative numbers on the diagonal here. So once I have this factorization, I know that my quadratic form is the sum of squares. The first square here is the square of the first coordinate of R multiplied by the input vector X, which would come from the first row. 3x minus 3x1 minus 2x2 plus 5x3 quantity squared. In my second square, I have the inner product of the second row of R with x1, x2, x3. So that'll be x2 plus 8x3. And then my third square here will be just 6x3 squared. So this is the sum of squares because this matrix is factored as the Gramian of R here. And also I know in this situation that S has to be positive definite because R is non-singular. It's upper triangular and none of the diagonal entries are equal to 0, so this has to be a non-singular matrix. So that's our first example of a Cholesky factorization.